Hey, welcome to my series in parallel circuits introduction. Circuits set up in parallel and series have fundamental properties they share, but also things that distinguish each from the other. In addition to this, different elements are affected differently by how they are arranged. You may recall that capacitors, when calculating the total capacitance, the formulas are the opposite for capacitors in parallel and series compared to resistors arranged in the same way. Safety is also at mind when designing and manufacturing products. Internal circuitry plays a big part of how appliances and electronics function. The series circuit. A series circuit is defined as having only one path through which current can flow. From this definition, three rules of series circuits must apply. All components share the same current, resistance adds to equal a larger total resistance, and voltage drops add to equal a larger total voltage. And the formula is R total equals R1 plus R2 plus R3 plus Rn. Application: the microwave. Microwaves, which utilize microwave radiation to heat food, can be potentially dangerous to humans if directly exposed to this radiation. Part of the design process was to ensure people can operate the microwave safely. The way they did this was by utilizing a series circuit in which multiple safety sensors must be engaged to the correct setting for the power to be supplied and for the microwave to operate. One example of this sensor that only engages when the door is closed. The parallel circuit. A parallel circuit is defined by having multiple current paths through different nodes that will all end back at the same node. All components share the same voltage. Resistors diminish to equal a smaller total resistance. Branch currents add to equal a larger total current. Those are the three rules. And the formula is R total equals 1 over R1 plus 1 over R2 plus 1 over Rn, and so on. Application: lighting. In buildings, lighting circuits are almost always wired in parallel, which has multiple benefits in comparison to series for this application. The main reason is bulb brightness will stay the same for each individual light bulb, as they all share the same constant voltage. Also, if appliances, lights, electronics, etc. were to be set up in series, many appliances towards the end of the circuit will simply not work, as not enough current will reach them. In addition to this, if one light blows, you don't want the whole building to lose power, which is what would essentially happen if all appliances and lights were set up in series with each other. This is a worked example, calculating the total resistance and total current. So we have our example. It's just 4 different resistors, 2 of them are in parallel with the other 2. So first we need to make the circuit a series one. So by doing this, we can see that 1 and 2 are in parallel and 3 and 4 are in parallel. So basically what we do is just add those up. 1 and 2 in parallel plus 3 and 4 in parallel. So to find the Rx, which is 1 and 2 in parallel, we just do 1 over each resistor, 1000, plus 1 over 250, the other one. And that will equal 200 ohms. And then for the Ry, which is 3 and 4 in parallel, we do 1 over 3500 ohms plus 1 over 250 ohms, which will give us a equivalent value of 189.18 ohms. So then to find the R total, once we've basically made this just a series circuit with 2 resistors, one here and one here, we just add them up. 200 plus 189 is 389.18. So that's our equivalent circuit with 1 resistor to these 4. So that's the R total. So to find the current drawn of the total current, we just use Ohm's law, I equals V over R, which would be 24 volts over 389.18 ohms, which is our total, which will give 0.06 amps drawn. And yeah, thank you for watching.